Dużo obsunięć jest. Hello ladies and gentlemen, welcome to our lecture for today. First of all, I would be grateful for response. Can you hear me? Is everything okay? Please respond on chat. Okay, great. So today's lecture, it will be focused on general, because so far during this semester we have covered general ideas of model building, ideas of how to construct from a model, how to simulate a model, how to implement it in Stan, but really we need to now focus a bit on what is going on in those models. That is, what actually we are computing. And for that, we need to do a bit of theory to explain how really perform computation of Bayesian models in order to get results that we are interested in. So we'll focus on generally managing expectations that are present in our computation. So what is really a point of all the computation in the Bayesian framework is to compute the expectation of, I'm trying to move the camera, but it is not cooperating. Okay, now it is. Okay, I had to move into the different corner. The main point of our computation is to determine the expected value of certain functions of random variables. And this very general term covers all kinds of statistic functions that allow you to get some information about the model, about considered variables, and it is a property that has many benefits. This is the very useful quantity, the expectation, because it is easy to compute and you can do a lot with that. So, what is expectation? Well, if we have some kind of function with not especially strong requirements regarding regularity, we can say that one function given of a parameter that is some variable q belonging to a parameter space large Q, expectation of this function value with respect to probability distribution, that is the probability distribution or probability mass function of parameter q, has an expectation given by the following definition. That is, in case of continuous variables, is an integral over values of parameter q of the product of function of parameter q and the probability distribution function. This integration is of course done over a set of possible values of q. In discrete case, this is similar situation, but we are now summing over all possible values of Q of the product of function of Q and the probability mass function of Q. So in discrete case it's much simpler. The main problem in getting these expectations is that in practical case neither those integrals nor those sums are not computable, because distributions are either not available in a closed form or they are very difficult to analyze. So one of the main ideas being used in the statistical analysis is using the model estimators. That is finding the maximum or maximum a posteriori, maximum of the posterior of the probability density function or mass function in the discrete case, and selecting this as an estimate of expectation, which is not necessarily a bad idea, because this can work for many distributions that are central enough, that are because in many cases expectation is close to the maximum. The best case is of course normal distribution, which is when the maximum and the expectation are equal. So we are using numerical optimization to find such maximum of the probability density function. And in case of well-behaved distributions, where there is not much skewness, not much problems, the actual expectation is rather close to the mode, so such approximation is usually enough. However, in more complicated distributions that are not characterized as well as mean and variance, then mode can be rather far away from the mean, because function has, the probability density function can have very complicated geometry that has multiple local minima, maxima, or is just very skewed to one side, where there is a maximum on the boundary but the tails are heavy enough so the mean is completely somewhere else. So this is the case. So the one example I like is the distribution of salaries in Poland, where we have a mode of small salaries in the service sector which is dominating, and it's far away from the national average, so the expectation of the expected value of the salary in Poland. So in case of model estimates, we can have problems with skewed distribution, which has maxima far away from expectations, and also we can have problems with uncertainty quantization, because we are essentially summing up the entire probability distribution with one point, its maximum. And we do not get information from that regarding the entirety of the distribution, its tails, its asymmetry, etc. Also, of course, the problem is multimodality, because when the distribution is multimodal, then finding the maximum is not obvious, and moreover, determining which of the local maxima is global is even more non-obvious. So what can we do? We can of course improve on the mode by creating some kind of the approximation of distribution in order to get some kind of uncertainty quantization. And this idea is not a new one. This is an idea proposed by Pierre-Simon Laplace, one of the inventors of model probability, who proposed the approximation of probability density function using the Taylor series expansion, but not of the probability distribution function, but its logarithm. In case when we approximate the logarithm of the probability density function using Taylor series, we can have the following construction. This construction says that our assuming that our logarithm of probability density function at point point Q is can be approximated as a logarithm at the mode plus first term disappears because the derivative at the mode is equal to 0 because it's a maximum, and then we add the second derivative. So it describes the difference, the quadratic form with respect to distance from the mode on the Hessian matrix of the logarithm of P of Q, computed at Q star, so computed at the mode. So we create quadratic approximation to the logarithm. And why this is in any way beneficial? Because after exponentiating it, we create an approximation of density, which is actually a normal distribution. A normal distribution with a mean at the mode and the covariance matrix equal to the inverse of the Hessian matrix at the maximum. So it allows us to create the appropriate distribution approximation, giving us the its normal approximation, and then we can compute the expectations of our function using formulas for expectation of our approximation. What is beneficial here is that we do not have to include the function we want to compute the expectation of in our initial computation of the mode. We work only on the probability density function, and then using this approximation we can work on any kind of function of parameters, which can be again beneficial because those functions are varying and might be have different quantities of interest. So this is a way to compute it. Normal integrals are actually relatively easy to compute. This is a well-known probability problem, so this is a good idea. And the only problem with Laplace approximation is that this is a local approximation. The approximation of the probability density function is valid around the maximum, where it can be well determined by the Taylor the logarithm of the probability density function can be well approximated using a quadratic form. The further away we go from that point, the further away we go from the quadratic approximation. And of course, normal approximation will create us very regular geometry that is related to the normal distribution. If we do not have such situation, then well, we have a bigger problem. So that's a way. This is a approach that is conceptually very easy. In McElrath's book, Statistical Rethinking, about a half of the book, all the examples are being computed using the Laplace approximation, which is not a, again, bad idea for simple distributions where there is no issues with geometry, no big problems. Then of course this can be used. So if we have something complicated, then what? Well, we can start doing some computation numerically to compute the integrals directly from the definition. So to compute the integral of arbitrary function of density function multiplied by the function of interest. And in numerical computation we have quadratures. Quadratures are known ideas how to compute the integral of given function, and for one dimension, so we have if our parameter q is one-dimensional parameters, it is relatively simple and well understood problem. First of all, we have very good quadratures for bounded intervals, so using interpolation quadratures or Gaussian quadratures. We can use adaptive quadratures if we expect that function is weird. To sum up, quadratures, very simple in one dimension, either interpolation on bounded interval or dedicated solution for unbounded intervals. Unfortunately, in higher dimension it's not that simple. Because in one dimension generally we have one simple grid that is the comes from the points distributed on an axis. However, the issue is that when there are more dimensions, then supplanting function appropriate grid for integration becomes heavily reliant on the geometry of the probability density function that we want to integrate. And in case of if the function has regular shape, then we can find that points evaluated as certain elements are easier to find, and also points evaluated a grid contribute to the integral, and a lot of points on the function contribute to the integral. If the function is very complicated in its geometry, then there might be issues in finding the distribution, in finding the appropriate points in the parameter space that contribute to integral. So we are computing function at points where the distribution is essentially zero. So we use computational resources to compute in the points somewhere here that are not actually contributing to the expectation because their values are very small. And the bigger question is what actually contributes to the expectation. And our intuition from the one-dimensional computation suggests that when we are integrating function, the most important points are those points where the function is large. So the closer we are to the maximum of the function, the more important those points will be for the integration. And what is important, that the probability distribution function always integrates to 1. So it will be varying values, but still the sum of the actual integral integrates to 1. So there will be points where the function, especially on an unbounded intervals, will be points where this distribution will be very close to 0. And when we look at the probability density function, generally transforming it to a space of distance from the maximal value, the density function will be decreasing away from the maximum. Because again, it has to integrate to 1, so it has to be a decreasing function. So here are the most values. However, that is only one piece of the puzzle, one piece of the computation, because we are integrating over a certain volume, and this volume is this volume is being difficult to comprehend when we look at it in a one-dimensional case. Because in one-dimensional case, when we divide our integration interval into 3 parts and we focus on the middle, we will lose certain parts, but if function is small here, limiting ourselves to the middle third only drops us 2/3 of the volume, which are perhaps not really relevant. However, when we increase the dimensionality, then if we limit ourselves to a middle, in 2 dimensions, we are now not dropping only 2 parts from here, we are dropping 8 of them. So now 8 areas are not being concluded in our integration if we limit ourselves only to a middle. In 3D it's even more complicated, because now there are 27 boxes here. We are using only one, so 26 boxes of identical dimensions are being ignored when we are focusing on such situation. This is a geometric complicated progression that shows us that we are, by focusing ourselves near the mode of the distribution function, we are dropping a lot and a lot of volume. And our integration is actually, we can say, a sum over values of function and pieces of volume corresponding to them. And in higher dimensions, the higher we are, the further we are from the maximum, the volume rises, because the localization near the mode, like us here, limits our volume. When we move to the or move away, the volume rises. So when we are getting further from maximum, there is more and more volume to account of. So because we have to integrate over all dq. So the product pq times dq looks somewhat like this. And because it looks somewhat like this, then the actual values that are important are values that are not close to the mode, because they are not contributing, because there is so little volume for them. So here's a little volume, and here's much more. So we have to move away from the maximum. Of course, not so far away that the product density function is completely becoming zero and the volume is irrelevant. But when volume rises, the points in the distribution function that we could think as not important are being more and more relevant for our computation. So this area where there is a let's say a compromise between probability density function and the volume it covers is being called a typical set. Typical set is the set in the the parameter space which contributes the most to the computation of the expected value. And this problem is being called concentration of measure, because our typical set is not really precisely defined. We cannot determine its boundary. It's more a fuzzy surface that is located the further away from the higher the dimension, the further away from the mode it is, and the more the higher the dimension is, the more it contributes to the expectation, and finally to really cover almost all the relevant probability in our computation. So we would need to integrate over the typical set. The problem is that we do not know what the typical set is, because it cannot be computed directly, because such computation would be generally more difficult than computation of expectation, which is, let's say, the problem that we are facing anyway. So we do not know where to integrate in the typical, so we could cover entire typical set, so we have a big problem. We do not know where the typical set is, and because of that we have problems with computing the integral, that is, or in other words, the approximation of our expected value. However, assuming that we can get samples from the typical set, then we can very well quantify the distribution behavior. because sampling the typical sets allows us to get the most important behavioral distribution. If we could compute those points deterministically, know what the shape of the typical set is, we could just get points from here in any way, that would be great. Unfortunately, it cannot be done. So we have to get samples from the typical set. And this is actually good information because using samples from the distribution we can compute expectations. So sampling our probability distribution, we will get most of the samples from the areas that we are really interested in, as long as we properly sample. And this is a bit of wheel definition, because when we start from one point we end another, generally we say that our sampling procedure is exact when our the mean of the samples, or the mean of the sample, asymptotically converges to the actual expectation. And it works not only for samples but also function of samples. So if we have average of the values of function of sampled parameters, and it asymptotically converges to the actual expectation, then our sampling procedure is exact. So that is our actual idea, to generate samples and get good get estimations of the expectations. And that gives us so-called Monte Carlo estimator. Monte Carlo estimator has a nice benefit that it is well quantified regarding the errors, because samples, the average is a sum of samples or functions of samples, and sum of independent random variables tends to become a normal distribution. So we can actually apply the central limit theorem to quantify the error of our sampling, because we can see that the distance for the between the estimate of Monte Carlo estimator and actual expectation is a normal distribution with zero mean, and the variance all equal to the is the standard error given by a Monte Carlo standard error, which is actually a square root of variance of our function f divided by n. So it's an estimate. It can be constituted as a Monte Carlo standard error. So we have the estimate of the error of our estimator and generally we can conclude that our Monte Carlo estimator is approximately normally distributed. So estimate of our expectation of interest. So we have a function of parameters that we want to compute this expectation, and by using an average of samples from the distribution of interest, for which we computed the function values, is normally distributed with the mean of expected value of our function and the standard deviation being a square root of variance of f, and this is normally distributed up to an order of n minus 3 divided by 2, and this can be negligible for n as low as 10. So generally we can assume that our approximation of expected value has just a standard error, given standard error. And this, of course, this standard error formally in this version is of course very difficult to compute, because generally requires solving a problem as complicated as computing the expectation. However, we can replace the estimate of the variance. We can replace the variance with its own estimator, and we can get the estimator of Monte Carlo standard error. So, assuming that this is an estimator of the mean, so the average of samples, we can create such estimators. And generally, we can quantify then how big error we have, and additionally for and this is computed very simply by simple statistics, the averages of samples. For small values of expectation, we can also use a relative error, which is the quotient of estimated Monte Carlo standard error divided by the estimated mean of the function. Because in this case, we can consider how big its error is relatively to the quantity of interest, which can be important, for example, in order to ensure the relative precision of computation. So how many samples we have to get the error, the relative error on level of alpha. And unfortunately, it can be a bit large, especially if we want a good precision. We will cover it in a moment. So, having that, what kind of functions really we want to estimate? What kind of expected values of function we want to estimate? And of course, the typical functions are like moments or cumulants, so mean, standard deviation of the variable, so we could get the actual value of interest. So for example, we want to estimate the effect of certain treatment on the population, and for that case we need to use, we want to have its expected value and also have its standard deviation. And for both those quantities, so the expected value and standard deviation, so the mean and standard deviation, we can create Monte Carlo estimators which will have their own errors. So they will just increase the uncertainty over our initial values. So that's one thing. Other thing are even probabilities. If you remember from the probability course that you had earlier, the probability of an event is again an integral over the certain set of possible values, and we want to compute the probability of certain of value of the function being in a certain interval or area in space. So this is an event. Also, statistical functions that we are interested in are histograms, which are effective summaries of one-dimensional marginal distributions. So, for example, to get some kind of uncertainty about the function of interest, we have the maybe less known to you, but empirical cumulative distribution functions, which are a certain complement to histogram, where histogram is like a probability mass function, probability density function, depending on what we do. ECDF is kind of like the cumulative distribution function. Both of can be computed and get some kind of knowledge about functional behavior. And of course, finally, quantiles, which are generalization of event probabilities, but we are often interested in values of what kind of value it corresponds to a given probability. So, for example, what top 10% values have, what value is of the boundary of top 10% values, for example, or what is the median? So, what is the samples are all function parameter values are being less than the point for which the parameters are equally probable to be higher or lower than. Okay, and as I mentioned, the most known moments are of course mean and variance. You might have heard about skewness and kurtosis, which represent how much asymmetrical the distribution is, and that's the general point here. Also, there are cumulants which are very similar to moments but slightly different, more used in the typical statistical computation. For the probabilities, actually, the situation is much simpler than we could think, because if we are interested in computing what is the probability that certain value belongs to a given interval, we can compute it by computing an expectation of a specific function, that is the indicator function. Indicator function of a set or an interval is a function that takes value of 1 when the element is in the given set, and value of 0 if the value is not in that set. So it's a very simple function. For example, for an interval, indicator function of 0, 1 interval would be a function that between 0 and 1 assigns, for x between 0 and 1 gives 1, and for x outside of the interval gives 0. And expectation of that function given probability distribution is actually the probability of that parameter given by this distribution function to be located in this interval. And what is the simplest thing about it is that really computation of indicator function reduces to counting the number of intervals that is in the given counting the number of samples in the given interval and dividing it by the total number of samples. So expectation of the indicator function, which is again probability of f belonging to the interval delta f, is the expectation of the indicator function. This is inequality. This is true always. However, the estimator of the indicator function, as using the Monte Carlo estimator we've defined before, is the average of values of indicator function computed at given values of samples. And because this always results either 1 or 0, then actually this sum will be equal to the number of samples that are being located in the set delta f divided by the n, and that will be our probability estimator. And probability estimator can be also given an answer to estimate, because it can because it is a binary event belonging to a set or not, has a following Monte Carlo standard error estimator, which is the estimated square root of estimated probability times 1 minus estimated probability divided by n. And similarly as previously, relative error can be a very useful quantity, for example, because it allows us to estimate the values of how many samples we need to get a small Monte Carlo standard error. And it is important to know that when the probability p is small, so the event is unlikely, the relative error will rise, because it's inversely proportional to the square root of that probability. So as long if p is small, then to get relative error small, we need to get n large. For example, if we have an event of 1% probability and we want to have a relative error of 5% of that, so 5 times 10 to minus 4, of probability, then we need a sample size that will be significant, because it will be, after squaring an appropriate computation, we will get that our relative error, our number of samples should be almost 40,000 samples. So small probabilities, but generally it should make sense to you that if event is unlikely, we should know more about it to give the informed quantification of how unlikely it is. Because if event is likely, we know like on 10 samples 3 of them happen, so this is like around 30%, those changes won't be that significant. However, if the event is unlikely, then we need to do a lot of more samples to precisely quantify how unlikely it is. The function that you normally do not think as a function, but more as a visualization technique, is a histogram. And histogram really is a probability estimation done for the entire space split into intervals or subset. Usually histograms do not go over the second dimension, but they are theoretically possible, but highly ineffective. So generally, the entire analysis is similar to the previous one, because the histogram is the task of our probability estimation here. And histogram is an interesting function because usually we can normalize it in multiple ways. Either we cannot normalize at all, so we just can give you the number of counts of certain events in areas, and this is, from probabilistic point of view, not as that useful, because those values are not interpretable too much without context of how many samples were given anyway. Or we can divide values by the number of samples. In that case, our histograms becomes the estimator of a probability mass function. So it becomes like assuming that our problem can be divided into a given number of intervals, then our function of our histogram will be generally a probability mass function, so a function that assigns probabilities to given intervals, and although sum to 1. Different situation is normalization to become similar to the probability density function. In that case, the integral of the histogram has to be summing up to 1, and that is not necessarily that's interpretable as previously. But it gives you values that correspond to the actual probability density function. So all of those are useful, but require different analysis. Finally, the companion to a histogram is the empirical cumulative distribution function, which is generally, in a way, an estimator of the cumulative distribution function. And ECDF is something that is easiest to define meaning by code, because it is a very simple function that just assigns probabilities to the intervals between minimal observed value and current observed value, and you can compute it very simply by sorting the values you have, and then adding sums of how many samples are less than the given sample. So assuming that that values are unique, this is very simple. If values are not unique, then you need to compute that in the rare case that two values of x are being repeated, then you need to compute a situation what happens then. But really the uncertainty in this case is comes from the estimation, because ECDF estimates not each point, quantities for each point, but it estimates the entire interval, how likely the value is less than this one. So the further away from initial value, then the less uncertainty is being present. Finally, quantiles, those are computed as an inverse problem to determining probability of interval. So really, we need to solve the problem of finding such p that probability of the interval is from y of minimal value to the value of p that we're being interested. That is here. So in order to compute that, usually we just find such point that, for which the number of samples is larger than or smaller than. In case if it is not possible, because for example we have odd number of samples, we use some kind of interpolation to find a point that will be between those two that we cannot find a point between. So we know that having samples from the distribution, we are in a comfortable situation that we can compute multiple functions of it. And computing functions of samples gives us a tool to compute the expected estimators or expected values of those functions, which is really what we are interested in. Because again, we want to, for example, estimate the certain parameter, so the expected value, and some uncertainty. We want to estimate potential profits, so a bit more complication. This function can be more nonlinear. For example, our model has multiple parameters. We are interested in a function of those parameters that corresponds to profits, like sum of sales, estimated sales, and estimated losses. And this function will be the function we are interested in. So again, we want to compute the expectation. And depending on what kind of function, we have multiple options of such computation. But we still have the problem that we need to have samples from our original distribution. And this is not really that simple. First of all, getting something random is not that obvious as you would think. There is an entire class of products called hardware random number generators, which are generally some kind of electronic device that generates a lot of noise. For example, an electronic lamp that was used as a precursor of transistors, not those ones that in audio, the more specific ones, and those generate noises which are being then transformed in a way to get a limited band and stuff like that. And it generates, for example, random numbers between 0 and 1. Other option is a software solution, which is a pseudo-random number generator. And pseudo-random number generator is generally a formula of generating a sequence that would have low autocorrelation, have a long period, and has a uniformly distributed quantile of numbers. What does it mean? It means that low autocorrelation is that there is a very small or preferably negligible dependence on previous values on the current ones. It is a function that will have a very long period, so the likelihood of returning to a given value is very, very small. Or it takes a lot of time to get it, so in that case the predictability of our random number instant will not be that high. And finally, uniform distributed quantiles give us that the generated numbers will be almost uniformly distributed. And like the simplest possible way to generate the random numbers is the so-called linear congruent recurrence, which uses the congruency concept. That is, we have the function that is computing modulo of certain linear combination of the previous number times a plus c, and computes its modulo given m. Of course, a, c, and m are usually primes, or at least relatively prime to each other, so the returns won't happen quickly. And what is also important, that this of course generates the sequences of natural numbers, and that is not a big problem, because of course you can always divide it by a limiting number and you get the 0-1 interval probability. Those are the simplest way. The appropriate selection of parameters gives you some kind of random number generator, but not that good. Again, the problems of autocorrelation, the periods, and like that. So this is something that can be easily retraceable. Currently, most widely adopted algorithm is so-called Mersenne-Twister algorithm, which is very complicated. I recommend you to reach to Wikipedia website about it, so you can get some more info about it. There are now some newer solutions, but the Mersenne-Twister is the most widely adapted and most implemented into most programming languages. So this gives us a tool to generate random numbers between 0 and 1. But we want to get samples from an arbitrary distribution, and that becomes more complicated. Fortunately, especially for one-dimensional distributions, it is doable, because our continuous our cumulative distribution function maps the parameter space X into a 0-1 interval, of probabilities. What happens that the value is less than or equal X. Quantile function, for all practical matters, is an inverse of cumulative distribution function. So having a quantile function just says, given probability of P, what is the number under which all values would be lesser than that to get that probability. And why we want quantile function? Because when we generate a number or a sequence of uniformly distributed numbers on given interval, then the sequence of quantile functions of those parameters is a sample of distribution for which the quantile function behaves. So, because CDF maps from X to P, so the probabilities, quantile function maps from probabilities back to X, so getting samples from 0, 1, so uniformly distributed probabilities, we get the sequence of values from our original distribution. And that's one option. In a different option is which one I mentioned on a few lectures ago, a grid approximation, so just approximate the probability density function with some kind of probability mass function that you can easily sample from. Either way is okay. Unfortunately, either way works really well in one dimension, but we can get the idea, because fortunately in this case dimensionality does not matter that much, either within one dimension or multiple dimensions, because the idea is generally the same. And we will do a few examples to get the general idea how the sampling works and what happens and what kind of errors we can observe in our computation, and how the Monte Carlo standard errors behave, and the quantification of our error. So we'll go through normal distribution, then we'll use, which gives us samples from real numbers. Then we will use a link function to see how normal distribution behaves for 0-1 intervals. Then we'll go through some heavy-tailed distribution, starting with Cauchy distribution, which is a special case of student t-distribution, and student t-distribution with finite and infinite variance. Cauchy distribution is a very nasty distribution that not only doesn't have finite variance, but even doesn't have a finite mean. So, if we want to estimate the expected value of a normal distribution by sampling from a normal distribution, we can see that increasing the sample size, we will get a reduction in the uncertainty. This is a ribbon plot representing the quantiles of our function, and we can see that sampling from the normal distribution will give us closer and closer to our mean. And when we compute the histogram, we can now see how that the histogram also is something that has an uncertainty. This is something that you usually do not see in histograms, but this histogram is the estimator of is the probability estimator. So it estimates the probability density function, and we are not certain where those samples behave. We can compare that with the actual density function and see that everything generally works out, that our samples are relative here, but again there can be some errors, especially that we have very small bins, so those probabilities locating values here are relatively small. Especially that changing the bins changes the behavior of the histogram. The wider the intervals, smaller uncertainties, because the probabilities of each interval are generally larger. In case of having them too fine, then it becomes very noisy with very high uncertainty. In case of empirical cumulative distribution function, we can now see how it behaves depending on details. We do not tune, because it like bins itself automatically, because it depends on where the samples are, and you can get the expected cumulative distribution function from our samples here. But that was a simple normal distribution. If we move something else, so for example we want to constrict our interval to the our samples to the 0-1 interval, so we have a function of a random normal number, so we can use an inverse logit function, or the also xpit function, that will transform from real numbers to 0-1 interval, and it looks like this. You can easily see that if x is minus infinity, then this is 0, so it's x is infinity, then this will be 0, and it will be 1. If x is minus infinity, then it will be infinity here, so this will be 0, and all values between will give some numbers inside. And as we can see, sampling normal numbers by transforming them, we will then see how the constriction behaves where the functions are being focused, and our distribution is no longer symmetrical, because samples also were not symmetrical, and moreover transformation between from real numbers to 0-1 intervals gives a more complicated function, which can actually be computed analytically and we'll probably do a scaling compared with one another, and in that case we can see that it is of course consistent with analytical result. And using sampling to verify analytical results is not a bad idea in general. So this is something that can be considered. Bigger problem comes when the distributions are more weird, and one case of such weird distribution is the student t-distribution. Student t-distribution is very useful because it is so-called heavy-tailed distribution. So it allows us to model events that in certain rare cases something weird or uncharacteristic can happen. Normal distribution does not have that efficiency, because that property, because when we introduce a highly different sample to our analysis of normal model, then we will have the have strongly disturbed our estimates of normal distribution parameters. Student t-distribution does not have that problem. Unfortunately, it gives different problems that almost no computation can be done analytically. And well, usually normally we use numerical computation, but in computation using normal distribution, we can use normal distribution properties to simplify computation drastically and get results much faster by solving simpler problems just by using certain analytical computation initially. What is interesting that student distribution generally has three parameters. It has the scale, location, and degrees of freedom. Location is generally location of the maximum of function. We don't say mean because it doesn't always exist. Location always exists, the values necessary, and we have the scale, which again is not directly analyzed the standard deviation of variance. Standard deviation can be considered a scale of normal distribution, but it gives us the potential range of values, and degrees of freedom is a very specific parameter that controls how heavy tails are. And it came from the traditional analytical computation that gave us the traditional analytical computation that gave rise to standards the student distribution by observation of repeated normal events, but in practice, originally number of degrees of freedom was considered an integer, but it doesn't have to be. The formulas work also for non-integer degrees of freedom, but the name state, despite that, it makes no sense if it's, for example, 1/2 of or something like that. Either way, the expectation and variance of student distribution is known because it can be computed, and as long as there is more than one degree of the number of degrees of freedom greater than 1, then the standard student distribution has an expected value of 0. If, however, number of degrees of freedom is 1 or less, and 1 is the case of Cauchy distribution, then the expected value does not exist. Mean is not defined. Similar with variance, as long as there are at least there's more than 2 degrees of freedom, then variance is well defined. It is defined for the interval between 1 and 2. It is defined, but it's an infinite, and for Cauchy distribution, so for 1 or less, it is undefined. And how it looks on the computation? Well, it looks like this. Cauchy distribution has heavy tails. That means that that it will sample normally, but sometimes it will introduce a new additional sample, which heavily influences how the average of samples looks like and its potential standard errors. And increasing number of samples will not help because there is no appropriate value. And this is an issue because generally Monte Carlo computation is based on central limit theorem. And because of that, we can analyze multiple samples and then get analyze, for example, the histogram of the estimator. So we can get we can simulate multiple samples for our distribution and then compute the value of estimator and then analyze histogram of that estimator. And we do not get a normal result, which should be generated if the central limit theorem would hold. And this is of course caused because we want to estimate the quantity that does not exist formally. Because you can always compute an average of samples and you get a number. But if that number estimates something that does not exist, it's a meaningless number. So in case of Cauchy distribution, we cannot use the estimator to estimate the mean because the mean does not exist. However, that doesn't mean that a function without defined mean cannot be useful. It can be very useful, but it is not useful for computing expected values, but it can be used for computing probabilities of events. So, for example, if we want to compute what is the probability of value of parameter being between -1 and 0, we just compute the expectation of the indicator function. And expectation of indicator function exists because it is a function of our probability distribution, not probability distribution itself. And as you can see, it converges very nicely, and the additional spikes do not happen here, because if a sample occurs outside of the interval of our interest, it does not change anything. And that's the property of heavy-tailed distribution, that you generate extreme samples, and they do not disturb the behavior in well-constrained intervals. And of course, errors can also be very well quantified. We can estimate the probability and get some kind of Monte Carlo standard error from that, and those values are reasonable and consistent with what we observed. If we increase the number of degrees of freedom, then mean is then well defined, which is a generally good idea, a good thing, because now, as we can see, it converges, but unfortunately we still do not have a good quantification of the uncertainty, because despite the fact that average converges to the mean, it is still not being normal. When we estimate the probability distribution of the estimator, so again we repeat the use of estimator on simulated data from this distribution multiple times and compute the histogram, it is not normal, so it's not consistent with the central limit theorem. So the central limit theorem in this case do not work, because again it would require for values to exist, so our estimator does not behave properly. Well, and of course probability estimates work. However, as long as we have more degrees of freedom, student distribution works very well, despite the fact that there might be occasional spikes. It is not that problematic. Those tails are not heavy enough. What is important? When degrees of freedom tends to infinity, student distribution becomes the distribution of because it's a normal distribution. And of course we can confirm central limit theorem empirically for this case. By repeated simulation we get results that we expected. So generally, we had a situation that we could see the problems happening here, and we knew that they came here because we generated the problem from the known distribution. However, if we create a probability model that is more complicated, that is more advanced, the probability distribution that is something that comes from multiple parameters, and we are just focusing on the quantity of interest, then we do not know what we can really expect, and perhaps repeated simulation are not a good idea in all cases. So there are methods of verifying or diagnosing our samples, what's going on. And one of the ideas is to estimate the tail behavior. So how heavy are the tails of distribution that we are generating samples of? Because if they are heavy, then we might have some problems with interpretation of our results. So for example, our expected values might not make sense. So because of that, we can use the so-called generalized Pareto distribution, which is a distribution that is a very simple distribution. It just has an idea that the function of interest is being the function of interest behaves as a power law. So in other ways, it's as a kth power of variableness. This should be x of z. Sorry, here. So we can actually use a classical statistical point estimator k hat as a test of tail behavior of the distribution. And we can fit k hat for tail of each distribution, and we get some kind of heuristic analysis that as long as k hat is less than 0.25, then we shouldn't worry. If k is bigger than 0.7, then we should really worry. And we can use it like this, that we just separate from our samples the middle, and then we compute the something that, like, we can get a bulk of distribution, and then we get the samples that, like, at least one estimated standard deviation from the center. And then we can see what's going on, and we can use that to estimate those left and right tail behaviors. And for our previous examples, we could see that for normal distribution there are no issues. There's even negative k hats. For student t-distribution with 3 degrees of freedom, there was also no issue. K hats were well below 0.1. However, for student t-distribution between values 1 and 2, so for 1.5 degrees of freedom, there was a significant k hats of between this 0.25 and 0.7 threshold, so something can be done with that with a bit of care. For Cauchy distribution, we are well above 0.7, especially in small samples, because in small samples it's even higher. The k hat becomes even higher. Takeaways from today's lecture. So, as long as distribution is not problematic, can give us very good estimates. We can, using Monte Carlo, we can get very good estimates and then quantification of quantities of interest. It should be noted that despite that we are estimating probabilities, those probabilities will be will have its own errors. If our samples are not consistent, or the distribution generally doesn't have right properties, there might be issues. But we can diagnose those even if we do not know the distributions, because unfortunately in complicated models we can get the we can get habitable behavior even if the functions do not normally look like they should have once. So by combining normal distributions in a not proper way, we can get a Cauchy distribution or something very similar to Cauchy distribution. While Cauchy distribution can be in its own beneficial, in other cases its results are very unwanted. This was very nice and all for small dimensions. The higher dimensions, the bigger the problems. We can relatively easily generate samples for one-dimensional distributions. We can relatively easily generate samples for multivariate Gaussian distributions. And for other distribution, unfortunately, we need to use something more, and those will be Monte Carlo or Markov chain methods, which will be discussed on the lecture next week. Are there any questions regarding today's lecture? We have a bit of delay on the on the stream, so I'll give you a few seconds to address that. Okay, if there are no questions, then thank you very much. Have a nice weekend.